Welcome! In this video, we'll be talking about electric dipole basics. If you want to see what's coming up, feel free to pause now, otherwise we'll just get started. Okay, so let's talk about what an electric dipole actually is. It's just a pair of charges, one positive, one negative, such that their net charge is 0. In other words, if the positive charge has plus Q charge, then the negative charge will have minus Q charge. So electric dipoles are important to study because, as it turns out, most things in the real world have a net neutral charge. However, they still can have interesting electrostatic properties. And so the most simplest, non-trivial case of net neutral charge is the electric dipole. And in fact, for example, in chemistry, you will actually hear it often said, like the electric dipole of this molecule, H2O, hydrogen bonds, all of that ultimately is electric dipoles. Okay, with that being said, let's actually get into the physics of this thing. And so the most important property of an electric dipole is called its electric dipole moment. And for whatever reason, it's represented with the letter P. So to calculate this, you take the displacement vector from the negative charge to the positive charge. I'm going to call it D. And then you just multiply it by Q. So this gives us what the electric dipole moment is for an electric dipole. Okay, so that's pretty simple. So now let's actually talk about how electric dipoles interact with electric fields. The thing is, it can get quite complicated, so we're going to just talk about the simplest case. If we have a uniform external electric field, how will the electric dipole interact with this? And I think the simplest way to see how this goes is to actually walk through an example, so that we'll do just that and then talk about what we can learn from it afterward. Okay, so here we are. An electric dipole with the positive charge being 3 coulombs at 2, 1, and the negative charge being 3 coulombs at 1, negative 1 is in a uniform electric field of strength 2I plus J newtons per coulomb. Okay. So A, what is the electric dipole moment? B, what is the net force? And C, what is the net torque? So first, let's find what the electric dipole moment is, A. So this is pretty simple. To find what P is, we literally just do Q times D. And Q is 3. And D, in this case, is I hat plus 2J hat. So then this literally just becomes 3I hat plus 6J hat. And the units are the units of Q times the units of D, which ends up just being coulomb meters. So there you go. That's the electric dipole moment. Next, B. What is the net force? So we want to draw what the actual forces on this dipole is. So there are two forces on this dipole. There's the force on the positive charge and the force on the negative charge. And I'm going to label the one on the positive charge F1 and the one on the negative charge F2. So, to calculate F1 is going to just equal the positive charge times the external electric field, E. So this just becomes plus 3C times 2I hat plus J hat. In a similar vein, in newtons per coulomb. In a similar vein, we have that F2 is equal to Q2 times E, which is going to be negative 3C times 2I plus J newtons per coulomb. Now, clearly, if we add to get what F net is just going to be the sum of these two forces, then this is going to just end up being 0. So the net force on an electric dipole in a uniform electric field is going to be 0 no matter what. One way of thinking about this is that the net charge of an electric dipole is 0. So if you have a uniform electric field, then there should be no net force on this net charge. Okay, now C is where things get a little more interesting. What is the net torque? So I'm going to just copy this diagram and move it down below to talk about this problem. Okay, cool. All right, so what is the net torque? So usually when you talk about net torque, you need to talk about rotating around some specific torque, some specific points. Like, this force will have a different torque depending on if you're rotating around this point or if you're rotating around this point. However, that actually turns out not to be true if the net force is zero. If the net force is zero, in classical mechanics, we get that the net torque is going to actually be the same regardless of where you rotate around. So because that's true, we can actually pick whatever place we want to be our rotation anchor. And so the simplest place we can pick to be our rotation anchor is actually right on top of the negative charge. So here is our rotation anchor in purple, right on top of the negative charge. Okay, now let's calculate the net torque. So the net torque is going to be the torque of the positive charge plus the torque of the negative charge. The torque of a charge is determined by its position compared to our chosen origin point, cross the force it feels, and the same with the negative charge. However, the position of the negative charge is 0 with respect to the center of rotation, so this R2 is literally just 0, and we can just completely ignore this term. Okay, so then all that's left is the R1 cross F1. So R1 in this case is going to just be our vector D from before, and the force is going to be what we calculated earlier. It's Q cross E, Q times E. So ultimately we get that the torque is going to be D cross Q times E. So let's actually just go through and calculate what this is. This is I hat plus 2j hat cross 3 times 2I hat plus j hat. This ends up being I hat plus 2j hat cross 6I hat plus 3j hat, which ultimately is negative 12k hat plus 3k hat, which is equal to negative 9k hat. So ultimately, the net torque is going to equal negative 9k hat newtons times meters. Okay, so just as a gut check, a negative torque should mean it rotates in the clockwise direction, and that feels accurate. Cool. So there's actually a more succinct way of calculating what torque is. It turns out that the net torque is going to be equal to P cross E, and that's it. And we can see that from this step here. Here, we can actually move the Q to be with the D without changing its value. Like, this is a legal vector operation. And so Q times D, we've already seen this before, it's just P. So ultimately, the net torque is equivalent to P cross E, which is really nice. Okay. So that's how electric dipoles work, and the electric dipole moment. But we can actually generalize the electric dipole moment to work for any situation with net zero charge. So let's do that. So if you just have some random situation with a bunch of charges, Q1, Q2, Q3, Q4, let's say, then let's also establish that they have positions R1, R2, R3, R4, and I don't know, put the origin here or something. It doesn't actually matter then. then the electric dipole moment of a charge configuration, first off, only exists if the sum of the charges is equal to 0. Okay. Given that this is true, it's defined to be the sum across all charges qi times its position vector. And that's it. So, if we actually look at our original dipole example, we can calculate the electric dipole moment in this same way. If this is plus q and has position r1, and if this is minus q and has position r2, then we get that p is equal to q r1 minus q r2. And with some simple rearranging, this ends up becoming q times r1 minus r2, or in other words, q times the vector from r2 to r1, which is our d from before. So, something interesting is that the choice of origin does not matter here. No matter what origin you choose, you will get the same thing for p. So let's show that really quickly. Let's say you wanted to figure out what the dipole moment is, and let's say our origin, instead of being at 0, was instead at some other location. So like, let's say our origin of choice, which I'll denote O prime, was here or something. Then, if we have p, I'll start in the bottom left corner. If we have p, and this is equal to this sum, now the displacement vector, instead of just being Ri, is now going to be Ri minus the new displacement, the new origin. So this ends up being the same as this. We can just use the distributive property to split. And then we can further split the summation. And then by the distributive property, we can actually just take this and pull it out of the summation. Okay, oops, didn't mean to steal that. And then this section is just 0, because we have that the sum of all the charges is 0. So then this term ultimately just ends up being 0, and we can safely ignore it. So we get back out our original p. So, regardless of what origin you choose, you will end up with the same electric dipole moment. Okay, so that's cool, but why is this useful? Well, it turns out that the same two equations from before, F net equals 0 and torque net equals P cross E, both of these are still true when it comes to this new generalized electric dipole moment, as long as the external field is constant. If it's not constant, this does not hold. And we can prove this relatively quickly, so I'm going to just go through that. So we're going to just do it for the net torque. You can work through the net force one yourself if you want. So the net torque is going to be the sum of a bunch of torques. And each of the torques are going to be the position cross the force, because that's the definition of torque. But then the force is going to be Q times E by the definition of electric field. So Qi times E. And then we can rearrange and move the Qi to the other side of the cross product. And then using the distributive property, we can group all of this together instead. And this sum is exactly P. So then ultimately we get exactly P cross E. Okay, cool. So with this shown, now to really cement everything together, we're going to do one last example problem. And here it is. Consider the charge configuration at left. It is placed in a uniform electric field, Ex equals I hat minus J hat newtons per coulomb. What is the net force and what is the net torque? So this looks really complicated. But if we look at it for a little bit, we can see that the positive charges add up to 16. The negative charges add up to negative 16. So that means that this is, we can consider this to have an electric dipole moment. And since the electric field is uniform, we can apply the formulas that we know from before. So that means the net force is going to just end up being 0. But to find the net torque, we should probably figure out what P is. We should probably figure out the electric dipole moment. So to find out the electric dipole moment, remember that the origin we choose to calculate it doesn't actually matter. And in the end, regardless of what we choose, it'll cancel out. So for convenience, let's choose the origin to be in the center of all of these. Then to find out what P is, we're going to be taking the sum of Qi times Ri for every single particle. So this is going to be, starting from the bottom left, we have plus 1 charge times negative 1, negative 1, then minus 2 charge times 0, negative 1, plus 3 times 1, negative 1, minus 4 times 1, 0, plus 5 times 1, 1, minus 6 times 0, 1, plus 7 times negative 1, 1, and minus 4 times negative 1, 0. Okay, this is a lot. Let's figure out what the x term ends up being. The x term is negative 1 minus 0 plus 3 minus 4 plus 5 minus 0 minus 7 plus 4. And the y term is minus 1 plus 2 minus 3 minus 0 plus 5 minus 6 plus 7 minus 0. So if we actually evaluate this, we get that the first one ends up being 0, and the second one ends up being 4. So what we get is that P is equal to 4J coulombs times meters. Okay, cool. So now that we got what P is, we can get what the torque is just by doing P cross E. So this is for J cross I minus J. And this ends up just becoming negative 4K hat. So then our answer is that the net torque is going to be negative 4K hat Newton meters. And that's it. Alright, so that's the end of this video. I hope this was useful. If this was useful for you, please like. If there's anything that you have any questions about, comment down below, especially if I made any mistakes. And finally, if you're interested in seeing more of this in the future, please subscribe.